Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to the online data structure class. What we will be doing today is to start the first online lecture on chapter 7, which is on sorting. I will be discussing different types of sorting algorithms applied to different data in different states of organization and applications. In your lab as well, we will try to observe the performance of different sorting algorithms when data is organized randomly. Some of the data will be already sorted and some will be sorted exactly in the opposite of the desired order. By this manner, you will learn the different sorting algorithms which have different performance in these different situations. Fast and efficient sorting algorithms are applied for code optimization during algorithm design. For the preliminary introduction, process of arranging items in the list in a particular order is basically called sorting. Sorting is applied practically in almost every field of discipline. For example, for us, sorting list of test scores in descending or ascending numeric order, sorting list of students alphabetically by the last name, sorting students by GPA score, by country, by city. So basically, sorting process can be based on any alphanumeric values. Now, sorting algorithms can be simple or complex. They range from memory intensive to CPU intensive, and you can have trade-off between memory and CPU. There are advantages and disadvantages of all the sorting algorithms. Which sorting algorithm is best for you? It all depends upon the application where you want to apply, the number of data items, and the memory CPU resource you have at your disposal. The types of sorting algorithms that I will discuss are insertion sort, which is a sequential sorting algorithm where we shift data elements one by one. It has time complexity of order n square. Shellsort, also a sequential sorting algorithm where it works by comparing elements that are distant rather than adjacent. Basically, we allow exchange of far items. It has time complexity of order n square as well for the worst case. Heap sort, where we build a heap containing the elements to be sorted, then remove them in order. It has time complexity of order n log n on average. Merge sort, we repeatedly divide data into half, sort each half, and combine them. It has time complexity of order n log n on average as well. Quick sort, we partition the list around one element called a pivot, then sorting each partition and combine it together. Time complexity of order n log n it has on average as well. For our goals, we inspire to learn that there are different simple algorithms to sort that has time complexity of order n square, such as insertion sort, selection sort, bubble sort. Our main concentration will be insertion sort. We will learn that it is very simple to implement, very memory efficient, but CPU intensive. It's efficient for small arrays, but as the arrays get larger and larger, the algorithm gets less and less efficient. Please note that any sorting algorithm efficiency increases if the array is partially sorted, since it will reduce the total number of steps required to sort the array. There is an algorithm, Shellsort, that is very simple to code as well as runs in time complexity of little o n square and is memory efficient. The algorithm can be made more CPU efficient by using Hubbard's increments. Thus, the new algorithm then averages between order n to power 1.5 to n to the power 1.25. There are slightly more complicated order n log n sorting algorithms, which are basically divide and conquer strategy. If you have collection of n elements, we split the collection list into two subsets, which are list 1 and list 2. We sort list 1 and list 2 separately, then combine the two lists into one list, which will be our sorted list. Any general purpose sorting algorithm requires big omega n log n comparison. This means that big omega n log n is a lower bound for the time complexity of any sorting algorithm that is based on comparison. Now let's further discuss the preliminaries. There are basically two types of sorting algorithms: comparison sorts and non-comparison sorts. In comparison sort, the order of elements is determined by comparing the elements together, whereas in non-comparison sort, order of elements is determined by comparing with input properties. In other words, you compare all the elements against one standard. The order of complexity for non-comparison sorts is linear, is order n. In this discussion, we will look into different types of comparison sorts, which I have skimmed through already. Each comparison sort algorithm will be passed as an array containing the elements and integer containing the number of elements. We will assume that n, the number of elements passed to our sorting routines, has already been checked and is legal. Data will start at position or index 0 for all the sorts in our array. Let's further discuss insertion sort. Insertion sort algorithm comprise the following points. It consists of n minus 1 passes. For pass p equals 1 through n minus 1, insertion sort ensures that the elements in positions 0 through p are in sorted order. Thirdly, insertion sort makes use of the fact that elements in position 0 through p minus 1 are already known to be in sorted order. In pass p, we move the element in position p left until its correct place is found among the first p plus 1 elements. Let's take an example and look into the detail of the table. Here we have an array with 6 data elements. The elements are 34, 8, 64, 51, 32, and 21. We start by dividing the array in sorted and unsorted section. We put the first element as the only element in the sorted section, which is at index 0 of the array, and rest of the array is unsorted. As we can see here in insertion sort, we pick a key and compare it with elements ahead of it and put the key in the right place. In the original sequence, key 34 is at index 0. Key 8 is after key 34. Therefore, key 8 is compared with key 34. 8 is less than 34. Thus we swap the keys. Positions moved in this case is just 1. This sequence is after pass 1. Pass 2, we compare 64 with 34. 34 is less than 64. Therefore, we do not swap the positions of the keys. 0 positions moved for this case. In pass 3, we pick key 51. Now key 51 is less than 64. Therefore, we swap it. Key 34 is less than 51. Therefore, we do not swap any further. Positions moved in this case will be 1. Now in pass 4, we pick key 32. 32 is less than 64. Therefore, we swap it. Key 32 is less than 51 as well. Therefore, we swap the positions again. Key 32 is less than 34 as well. Therefore, we need to swap again. Key 32 is greater than 8. Therefore, we do not need to swap any further. Positions moved in this case will be 3. In pass 5, we pick key 21. 21 is less than 64. Therefore, we swap it. Key 21 is less than 51 as well. Therefore, we swap the positions again. 21 is less than 34. Therefore, we need to swap again. 21 again less than 32. Therefore, we swap it again. Now, 21 is greater than 8. Therefore, we do not swap any further. Positions moved in this case will be 4. Basically, the way of working is to select, compare, and swap. Now let's observe a snippet of insertion sort code. Here in the implementation, the function name insertion sort accepts 2 arguments, variables a and n. Variable a is an array of type element type. Element type is typedef to integer. Variable n is then of type integer. Inside the function, you have variables j, p, and temp declared type integers. Next, you have for loop where p is initialized equals to 1, then single increment up till less than number of elements in the array. Since you will be swapping the elements, you assign the element of index p, which is array A index p, to temp. Next, you have another for loop where integer j is initialized to p. Now, the Boolean condition j greater than 0 and array A index j minus 1 greater than temp. If either one becomes false, integer j will not be decremented and the loop terminates. If the two Boolean conditions are true, then line 4 and 5 constitutes a swap, where data element at index j equals data element at index j minus 1 and data element at index j equals temp. Since we have n square comparisons, in other words, because of nested loops and n swaps, the dominant term being n squared, therefore selection sort time complexity order can be observed as n square. Now what if array is already pre-sorted? The order of time complexity in that case will be simply order n. Let's look into lower bound for simple sorting algorithms. We need to remind ourselves that upper bound, which is the maximum time a program can take to produce outputs, which is the worst case scenario, and the lower bound, which is the minimum time a program will take to produce outputs, which constitutes to be the best case scenario. Let's discuss lower bound for simple sorting algorithm. An inversion in an array of numbers is any ordered pair I and j having the property such that I is less than j but array index I is greater than array index j. Maximum number of pairs you can have for any array of size n would be n times n minus 1 divided by 2, which is also the maximum number of inversions in any list or array. Swapping two adjacent elements that are out of place removes exactly one inversion. For example, you have 6 numbers in the following sequence: 34, 8, 64, 51, 32, and 21. You need to swap 34 with 8, then 34 with 32, then 34 with 21. Further, you need to swap 64 with 51, 64 with 32, and 64 with 21. Then 51 needs to be swapped with 32, then with 21. And finally, 32 needs to be swapped with 21. The exact number of swaps will be 9, which will be needed to be performed by insertion sort. We need to find an upper and lower bound for the sorting algorithms in order to find an optimal sorting algorithm. Insertion sort gives us an upper bound of order n squared, which is the worst case. There is order n other work involved in the algorithm, the running time of insertion sort in order I plus n, where I is the number of inversions in the original array. Thus, insertion sort runs in linear time if the number of inversions is order n. A reverse order list has the maximum number of inversions of order n squared. For a sorted array, number of inversions will be how much? Sorted array has no inversions. Thus, the average number of inversions in a permutation helps us to compute the average running time of insertion sort. The average number of inversions in an array of n distinct elements is n times n minus 1 divided by 4. For any list of elements L, consider list in reverse order L of R. The list of the example we did, number 34, 8, 64, 51, 32, and 21. The reverse list will be 21, 32, 51, 64, 8, and 34. Consider any pair of two elements in the list x and y, with y greater than x. Clearly, in exact one of the list L and the inverted list L of R, this ordered pair represents an inversion. The total number of these pairs in the list L and its reversed list L of R is n times n minus 1 divided by 2. Thus, an average list has half this amount, or n times n minus 1 divided by 4 inversions. This theorem implies that insertion sort is quadratic on average. It also provides a lower bound about any algorithm that only exchanges adjacent elements. Theorem 7.2 states that any algorithm that sorts by exchanging adjacent elements requires lower bound, which is the minimum time a program takes to produce outputs. It's also called the best case scenario, which is big omega n squared time on average, which can be proved that the average number of inversions is initially n times n minus 1 divided by 4, which is big omega n squared. Now each swap removes only one inversion, so big omega n squared swaps are required. A sorting algorithm makes progress by eliminating inversions, and to run efficiently, it must eliminate more than just one inversion per exchange. Now let's discuss Shellsort, which was named after its inventor, Donald Shell. It was one of the first algorithms to break the quadratic time barrier. Although Shellsort does not have the fastest running time of all the sorting algorithms, it is fairly competitive, decent size, you can do data sets of 5000 element size to sort. Shell algorithm works by comparing elements in the beginning that are distant rather than adjacent elements. The distance between comparisons decreases as the algorithm runs until the last phase. In the last phase, adjacent elements are compared. In other words, comparing elements that are far apart, then compare elements that are less far apart. By this manner, gradually shrink towards insertion sort. Shellsort is also called diminishing increment sort. Diminishing increment implies that distance between items or data that we are sorting decreases as we progress in sorting. Can also be called diminishing gap sort. In a sequence h of 1, h of 2 up till h of t is called the increment sequence. This is a sequence of increasing integer value which will be used as a sequence from right to left of increment or gap values. Any increment or gap sequence is fine as long as h of 1 equals 1. The basic idea here is that instead of sorting all the elements at once, sort a small set, such as, for example, every fifth element in the array. You apply insertion sort. Then every third element in the array. You apply insertion sort, and so on. Thus, we will be applying a 5, 3, and 1 sort. Do we always do a 5, 3, 1 sort? No. In general, shell sort will always work as long as the last phase is a 1 sort. For any increment, phase, or gap value h of k, we have array A with index I less than or equal to array A index I plus h of k. In other words, all elements spaced h of k apart are sorted. Conceptually, separate array into h of k columns and sort each column. The array is then set to be h of k sorted. Let's take a look at an example where an array or list contains the data elements in the following sequence: 81, 94, 11, 96, 12, 35, 17, 95, 28, 58, 41, 75, and 15. We have 13 numbers to be sorted. Let's choose Shell's increment 5, 3, and 1. For the fifth increment or gap, we will look at numbers 81, 35, and 41 and sort in order or swap the values such that we have the numbers as 35, 41, and 81 in the array slots. Then look at numbers 94, 17, and 75. Similarly, swap the values as well such that we have 17, 75, and 94 in the array slots. Finally, we look at 11, 95, and 15. and swap the values such that we have 11, 15, and 95 in the array slots. Once finished, we will be having fifth increment or gap sorted array as 35, 17, 11, 28, 12, 41, 75, 15, 96, 58, 81, 94, and 95. For the third increment or gap, we will look at numbers 35, 28, 75, 58, and 95 and sort in order or swap the values such that we have the numbers as 28, 35, 58, 75, and 95 in the array slots. Then we will look at numbers 17, 12, 15, and 81. Similarly, swap the values or sort it such that we have 12, 15, 17, and 81. Finally, we will look at numbers 11, 41, 96, and 94. Sort or swap the values such that we have numbers 11, 41, 94, and 96 in the array slots. Once finished, we will be having three sorted array as 28, 12, 11, 35, 15, 41, 58, 17, 94, 75, 81, 96, and 95. For the first increment or gap, which is the last increment of phase of Shellsort, is basically an insertion sort algorithm. Thus we apply insertion sort to the whole array or list and get the array sorted. The final sorted numbers will be then 11, 12, 15, 17, 28, 35, 41, 58, 75, 81, 94, 95, and 96. To better understand Shellsort algorithm, would the sequence 7, 3, and 1 be better than 5, 3, 1 we performed? Try it with the previous example and compare the number of swaps for both cases and judge for yourself which sequence brings you lower number of swaps to get the array sorted.